the creation which is around us. It's worth to protect, and finally we are part of it. And we are not above and not under, we are part of it.
That is why scientists intend to measure the health condition of our planet. They are shooting laser beams into space to find out how the climate is changing. How much ice is really melting? How much will the sea level rise? What will happen with nature and the environment, the plants and the animals? A lot of questions need to be answered. The stakes have never been higher.
Biodiversity and ecosystem preservation and food security and energy and mineral resources and just geographic locations and positioning is essential.
Imagine a future with driverless cars, planes without pilots, boats without anyone steering. These scenarios demand precision at the millimeter level. This future is right around the corner. Through millions of years, Earth has been in constant flux, moving slowly according to the laws of geology. But then humans came along and changed the rules. Today, our planet is changing more rapidly than at any point in its history. The consequences are dramatic.
I have 10 grandchildren, and I'm just wondering, I think almost every day, where will they end up? Where will they have their homes?
The sea dines on the land in so many ways.
As a citizen of Maldives, that's not something that I want to really think about, I guess. But if the current trends in the IPCC continues for the rise in sea level, there would not be Maldives in the future.
Many nations and cities are living at the mercy of the challenging climate situation. Some are virtually floating on the ocean's surface, such as the people of the Maldives. Wherever they are in the country, whatever they do, they completely depend on what's happening with the sea. That is why they are called the people of the sea. To ensure a sustainable development, we absolutely depend on knowing with the highest level of precision where we are and where we are going. That is why these laser beams are directed towards space, to determine exactly where the satellites are, so that they again can give us, down here on the ground, precise answers to where we are. But the scientists also need to know where Earth itself is located in the vast nothingness of space. That is why they are searching for signals from deep cosmos, to find a point of reference and use it to determine the position of the Earth. They are searching for the quasars, many billion light years away.
A quasar is intense radiation from a very compact region that is very far away in a distant galaxy. They are so far away that they do not move compared to the Earth. So we can use the quasars as stable reference points.
The more antennas we have spread out across the globe, the more precisely scientists can determine Earth's position.
They simultaneously observe the same source. And we compare the arrival time of the signal, and from this we can very accurately determine the position of these sources. And if we very accurately know the position of these sources, we can then very accurately determine the orientation of Earth in space, but also the distance between our telescopes on the ground.
Yet, despite help from quasars and satellites, there are more challenges that must be overcome to ensure millimeter measurements. Because Earth itself is a precarious planet, constantly moving, constantly changing. This causes difficulties in the quest for the absolute exact position. Scientists are therefore studying causes and effects of the many uneasy movements of the Earth. The science of this is termed geodesy, the science of Earth's position in space, its form, rotation, movement, and gravity field. Right outside Washington, D.C., in the United States, lies Goddard Space Flight Center, an observatory of NASA. Goddard is by many considered to be the cradle of modern geodesy.
Geodesy by nature is a global endeavor because you need to take measurements on a global scale. And while NASA has a system of satellites in space, geodesy is really about the ground. And so without this ground network, you would get a very incomplete picture. So they have to be distributed well around the globe and evenly distributed. And today they're not.
In the Northern Hemisphere, there are many geodesy stations. In the Southern Hemisphere, in contrast, there are only a few. One of them is located close to Johannesburg in South Africa, where Professor Ludwig Combrink and his colleagues have established the Hardrau station.
Okay, so originally this site was a deep space tracking facility for NASA, but now it was converted to an astronomical research facility, and part of what we do is space geodesy. There aren't any other stations such as this in Africa, and so we are what is called a fundamental site because a lot of the different techniques are co-located on the same site.
A fundamental site like this on the southern tip of Africa has now also been established in Norway, all the way north in Europe, in Ny-Ålesund on the island of Spitsbergen, only 10 degrees from the North Pole. In the past, this has been both a hunting and mining community. Today, it is a research station with wide international participation. Here, the Norwegian Mapping Authority has had an Earth observatory for decades. But the headquarters is back on the mainland, where the Mapping Authority for years has been using terrestrial sensors for the current GPS system. But there are more parameters needed to determine the precise coordinates. During the Ice Age, huge glaciers were pressing the land down, and when the glaciers melt, the land will rise. This land lift also needs to be included in the calculation when more precise positioning is called for. This is especially important when predicting how much the sea level will rise. The last few years have shown that in order to make such precise positioning, there is a need for technology that can take these measurements of the Earth from space.
That knowledge wasn't back home, so we need to go abroad, and we went to NASA, of course, and we find the knowledge that we needed because they have been in the field of space geodesy for many, many years. But as it is right now, the ground-based infrastructure is okay for those who want to navigate a car in the streets. But for those who want to measure the ice cap meltdowns and the sea level rise and things like that, we need to improve the accuracy.
There is a close connection between the ice caps meltdowns in the polar regions and the sea level rise in other parts of the world. Ny-Ålesund is a very sensitive early warning site for what's happening with the climate. That's one of the main reasons for establishing a new geodetic observatory on a little cape a few miles northwest from the small research village. Another benefit of establishing antennas here is that its location so far north makes it a convenient site for tracking the many satellites in polar orbit. In the summer of 2016, 2 huge antennas were put in place on this Norwegian ground, relying on guidance from the US, constructed by a German company and with Spanish builders. a truly global endeavour. With this new observatory, Ny-Ålesund will have a central position in the global geodesy network. But to ensure a truly global coverage, other parts of the world also had to be involved. Argentina, too, recognized the need for a geodesy station and decided to build a new observatory in a beautiful forest park between the cities Buenos Aires and La Plata. Free from vibrations in the ground caused by heavy traffic and free from cell phones and radio noise. The AGO station in the middle of this natural environment is a collaboration between Germany and Argentina. Director Hajo Hase himself is German, settled here to establish the station. But why so much work for some tiny millimeters?
Well, you can laugh about it and think this doesn't make big difference for my daily life. That is absolutely correct, and I think we are here working on a subject which is science-driven, but it has also a serious application, and the serious application comes by global change. We are all observing that glaciers are melting, we are observing that the sea level is rising, and now it comes back what science can supply for the prediction, how it will evolve in the future.
Scientists have for decades been studying the changes of the huge ice caps in the polar regions. And for years, scientists have stated that if the ice cap over Greenland melts, the sea level will rise 7 meters. But where? Which oceans are we talking about? And which countries will be affected? 7 meters is only a global average.
The average figure is camouflating to some extent what you will see in special area, because when ice is melting on Greenland, there will not be any sea level rise on Greenland, because the weight on the Greenland, because of the melting and runoff of ice, will make that the Greenland is coming up from the sea. The sea level rise will not be the same all over the world. The runoff from northern glaciers will affect the southern ocean, part of Pacific and the Indian Ocean, much more than it will affect the northern part.
Huge amounts of ice are now plunging into the ocean. Some of the icebergs breaking free are taller than the Eiffel Tower and the tallest buildings in Manhattan. A paradox, considering the millimeter precision needed to determine how much the sea level will rise because of it.
Ever since the last ice age, the global sea level has been rising by, say, 1 millimeter a year, approximately, over time. Now, climate change and global warming has now caused this sea level rise to accelerate. So for quite a while, it's been now 2 millimeters per year. Now it's up to 3 or maybe even 3.5 millimeters per year, and it looks like it's accelerating. This is very important knowledge, especially for coastal regions, for knowing the impacts of climate change. And you can just hear it's millimeters per year. If we don't have millimeter precision, this is not a question we can answer.
The truly big global geophysical forces such as winds and ocean currents, tides and gravity have been in existence since the beginning of time, and we have never needed millimeter precision to deal with them. Instead, we have learned how to organize our existence around them, and even using their tremendous forces to our benefit, like the people in Cornwall on the west coast of England. In the little portal town of St. Ives, the Atlantic is coming in and flowing out at a steady 6-hour cycle, regulated by the forces of gravity from the moon, the sun and the planets. People in this little fisherman's port have throughout the ages lived with, not against, the forces of nature.
You work around the tide. The tide doesn't work around you. You've got to work around the tide. It makes a difference to the fishermen in the fact that some days they will have to go to sea at 2 o'clock in the morning, and other days it will be 8, 9, 10 o'clock in the morning. It governs the day. They work around the tides because we are a tidal port.
The mainland and the mountains are also governed by the forces of gravity. Just like the oceans are being pulled in and out due to the tidal water, there is also something called earth tide. We are constantly being lifted up or lowered down without even realizing it, which complicates the measurements even more.
So if your measuring techniques cannot do millimeters, what are you talking about? And that's just a very complicated process because the Earth is very dynamic, the oceans are dynamic. What do you measure? People use, say, tide gauges to measure the ocean levels. But now what has moved, the land or the ocean? So the Earth is not a stable thing.
There are different challenges in different parts of the world. Africa is often struck by drought. Observations and precise determination of where to find water, also underground, is of great importance. A coordinate system that with high precision can locate such spots of water will be highly valuable. Another challenge in Africa is the lack of precise maps.
At the moment, in Africa, the countries are on different mapping systems. If you look at the map of Africa, you'll find that there are countries where there are no natural boundaries, for instance. Say between Botswana and Namibia, there is just this long line on the map. Now, if there is not a fence there that's been surveyed in and agreed upon, then it becomes very difficult to say, whose land this is. So you might find yourself either living in Botswana or Namibia, and who do you pay tax to, etc. It could be problematic.
But one thing is to know what is needed. Another is knowing what to do about it. To ensure safe navigation in our everyday lives, we need stable reference points to not get lost. Topographical clues, such as mountain peaks and other elements in the landscape. That is also applicable for measuring what is happening with the temperature. When did it happen? Where did it happen? And what were the circumstances?
If you want to measure how temperature change, you need to make a georeferentiation because the temperature in itself doesn't worth anything. You need to know where this measurement and when it was taken in order to give it a senseful meaning for the future.
At all times, humans have searched for such reference points in order to find their place in the universe. For a long time, the sun was their best guidance. A lot of the old stone monuments seems to have functioned as astronomical observatories, where the position of the sun determined location and direction. The modern world is now seeking, through the United Nations, a common coordinate system for all countries, based on the science of geodesy. They are searching for a GGRF, a Global Geodetic Reference Frame.
Bringing this process through the UN has raised the level of awareness of the benefit and the need for the Global Geodetic Reference Frame to our political masters in our home nations.
In order to enhance this sustainability of the reference frame, we need a long-term basis also in the UN. So this is very important, a very big step for the work ahead.
A GGRF, a coordinate system that can be considered an international necessity. Deep down, in the core of our home planet, there are enormous geological forces at work. Forces that are also affecting the surface areas where we reside. The big tectonic plates are moving. The continents are both drifting apart and coming closer together.
Australia is actually moving. Australia is moving north at about 8 centimetres a year, about as fast as your fingernails grow, which doesn't seem like a lot, but 8 centimetres a year is significant if you're trying to get precise positioning down to 1 or 2 centimetres.
The unstable, huge tectonic plates can also have disastrous consequences. Monitoring this seismic activity can provide early warning for volcano eruptions, earthquakes, landslides and tsunamis.
Japan is located in an area where 4 active plates are colliding. This makes the country prone to a lot of disastrous earthquakes and volcanic activities.
Natural hazards have disturbed human existence throughout history, and it will do so again in the future. But next time, we might be forewarned.
GGRF is essential not only to monitor crustal deformation, but also to recover from these disasters.
Natural disasters can strike everywhere, but some areas, such as the Caribbean islands, are struck on a regular basis.
We are so affected by natural disasters such as hurricanes and tropical storms, and it's very important for us to have the reference data to be able to respond effectively to these kinds of events.
The quest for the exact position reached a crucial point when the General Assembly in the UN on the 26th of February 2015 adopted a resolution concerning the importance of geodesy. It was the Ambassador Peter Thompson from Fiji who put forward the resolution.
We were very concerned at the possible impacts arising out of climate change, in particular rising sea levels and the way that these were impacting our coastal ecosystems, our coastal reference points.
In addition to the coastal regions, there are many other topographic areas that will be influenced by this, such as in China, the most populated country in the world, with mountain areas, midland landscapes and coastal regions.
You know, China is a big country. From the north to south, from the east to west, take a long distance. Without a coordinated system, we cannot connect. That's why a unified georeference system for China is very important.
And the GGRF seems to be of great importance for food security and more efficient agriculture in a world with a growing population and shrinking land areas.
Much of Australia's farming is moving into a precision agriculture space where we very precisely identify exactly where seeds are planted. We run tractors down exactly the same wheel ruts so that we maximise the production from our farms with the minimal application of fertilisers.
This precision is also crucial for self-driving vehicles, in which Australia is in the forefront.
If you've got a future where there will be self-driving cars, you need really accurate positioning to ensure that that cars aren't running into each other because their position within the lane is not accurate. So the GGRF will be really important for the whole of Australia if we're going to move into a future with this sort of technology.
In order to establish such a reference frame, all the different stations around the world must have to relate to the Earth's centre of mass. With that common ground, they can operate in a global scientific collaboration. By shooting lasers towards the satellites from different points of the world, they can determine the Earth's centre of mass and at the same time the position of the satellites and their orbits. Both the knowledge of geodesy as a science and the technological equipment needed on the quest for the exact position are important challenges for future generations. At the Harterau station in South Africa, they have taken on this challenge.
So if you can see here, the Earth is not standing straight, it's tilted. Ne? Do you know that planet Earth is moving?
Yes.
From which direction to which direction?
From that to that to that to that.
Someone said from east to west?
Not to west.
No.
At the observatory, for us, it's very important to tell the general public, school kids, teachers, about the science we do here, especially about geodesy, its applications and its importance.
I'm here to pursue a master's
And this is a great opportunity to get wide knowledge, and the team here is also supportive. Yeah.
I'm from India. I came here for doing my PhD, and I'm studying radio astronomy. And we have like a radio telescope, which I use for my study purpose. So it feels good.
Argentina has also taken the challenge of lifting geodesy into the public debate. At the University of La Plata, there are seminars about technology and the need for this new millimeter precision.
In my view, the main benefits are related to improve the knowledge of the territory. And most of the economy of Argentina relies on natural resources, and to get benefit from that kind of resources, you need to improve your knowledge about the territory.
The work to establish a global geodetic reference frame and the quest for the exact position is an ongoing process all over the world. From the smallest of scales to the enormous infrastructure of the big cities. Through this process of mapping the future of the planet, we are laying the foundations of global cooperation between nations and continents. Sometimes it's about land areas and industry. Sometimes about earthquakes and other natural hazards. Sometimes about driverless vehicles, or about climate change and food security. Other times, it's about our own simple lives. Even though our planet is both unruly and incalculable, scientists have taken the challenge of building a global geodetic community. An important part of this has been to include poor countries in the process.
Very obviously, the poor parts of the world will be suffering the most from climate change, whether drought or whether cyclones. So this is in the deepest interest of the developing world. But obviously there needs to be a global burden sharing.
No country can do it alone, definitely. That's very clear from the amount of work that needs to be done and the nature of it. Multilateral cooperation is critical for this GGRF to be successful.
My dream is that the result of the work we now do will make the United Nations member state agree on a convention to provide resources so that we together can make or give the world the global geodetic reference frame it needs, the accuracy, the sustainability.
A global reference frame is key if you want to be able to compare data from all continents, from Americas, from Asia, from Europe, and to empower scientists from all parts of the world to really give precise information to make the planet a better place.
And in this aspect, we have to study much more. We have to understand how nature is working, and we have to manage now that our children has also a future.